Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 24, and in this lecture we will be looking at the lowering of the Fermi level with respect to temperature. If you remember, in our previous lecture or discussions, we had looked into how the intrinsic carrier concentration changes with temperature, right? This is where we study how the Fermi level changes with respect to temperature. So, the outline of the talk is we will be looking at how the EF level with lowering in temperature, how does it change? We need to look into that. Look into therefore the mathematical structure of EF with respect to temperature. You must be already knowing degenerate and non-degenerate semiconductor. I will try to showcase that, and then we will look into the Fermi level and dopant freeze out at cryogenics, and then finally look at the bulk potential variation at cryogenic temperature. Right? So, this is the overall outline which we will be following for this course. Now, what we have learned, and this is quite interesting, is that if you remember in my previous talk or my other lectures also, you must have seen that we define the intrinsic Fermi level as a level which is somewhere between. So, EFI, the intrinsic Fermi level, is somewhere between the conduction band and the valence band by 2, half of it, right. So, exactly in the middle you will find the Fermi level here. This is known as the intrinsic Fermi level. When you did not do any doping, when everything was fine, the probability is exactly equal, then the EF value, EF referred to as EFI, intrinsic Fermi level concentration, will lie somewhere in between the band gap Eg by 2, and this will be approximately given by Eg by 2, right. What we have seen is that as the temperature goes on decreasing, the actual Fermi level shifts below the intrinsic Fermi level, right. And this you can correlate with my previous lecture, that as it shifts below, the energy difference between the conduction band edge and the Fermi level goes on increasing. Now, since it is a negative exponent, as the Fermi level shifts more closer to the valence band, the number of free electrons available to contribute to the charge carriers and give you a current actually drops down drastically. So, if you look at the Fermi potential phi f is given as ut is basically kT by q, thermal energy, and is given as natural log of Na by Ni, where Na is the acceptor ion concentration and Ni is the intrinsic carrier concentration, right. That gives you the value of your Fermi potential in this case, right. And that is the reason it is written on the right hand side, that if the decrease in temperature, the Fermi level goes away from the intrinsic Fermi level, right. So, I will keep it very bare basic to understand, give you an understanding of it. Now, as I discussed with you, the Fermi potential is now defined as a difference between the intrinsic Fermi level to the actual Fermi level at energy T, and is given by ut ln of Na by Ni, which is given as kT by q. So, if you look carefully, my phi of f will be equals to kT by q ln of Na by Ni, correct. Of course, as the temperature goes on increasing, this phi f value goes on increasing, right. So, when the phi f, which effectively means that your Fermi level at temperature T pushes down below, because as the temperature increases, this goes down. This is what I was trying to say, that as the temperature goes on, if you look at this point, the thermal energy also, ut also decreases. But please understand one important point here. The intrinsic carrier concentration, which you had found out earlier in my earlier lecture, right, decreases drastically with temperature. So, you see, let me go one by one and explain to you. See, the relative distance between the Fermi level and the conduction band gives you an idea about the number of charge carriers. However, look at the intrinsic carrier concentration. It falls down drastically lower as the temperature falls down. So, two things happening. One is your Fermi level moving away from the conduction band, because of which the charge carriers are getting minimized. Not only that, your intrinsic carrier concentration also falls down drastically at much lower temperature, and therefore this phi f increase even with the lowering of temperature. So, you see, if you lower your temperature, right, ut goes on reducing, but your Ni also reduces, which means this quantity goes on increasing. So, there are two opposing forces acting on phi f. One is ut, which is a linear dependency on T, and therefore, as the temperature starts to go down, UT value starts to go down, and therefore phi f linearly has to go down with temperature. It's a known fact, right? And nothing to worry about in that case. But we are missing one important point which we discussed in the earlier slides or earlier lectures, that Ni will also start to drop down. So Na by Ni term starts to shoot up. Therefore, ln of Na by Ni, the natural log of Na by Ni, starts to shoot up. So there are two quantities which is happening. One is UT going down, another ln of Na by Ni going up, right? What we have seen is that because of much larger fall in the value of Ni, the natural log of Na by Ni increase is much larger as compared to UT decrease, and therefore phi f actually starts to increase. Starts to increase means it is pushed down and down below the Fermi level. So please take this into consideration while discussion is going on, that phi f will go down, two opposing forces UT and Ni, and therefore phi f will actually be increasing with respect to lowering of temperature. Now let us look at the energy band diagram at T equals to 0 Kelvin, right. Now at T equals to 0 Kelvin, as I discussed with you, if it is an intrinsic one, we are doing anything about it, then it will be halfway between EC and EV for an N-type material, and halfway between EA and EV for P-type material. What we have seen is, let's forget about T equals to 0 Kelvin. 300 Kelvin, we know that the intrinsic carrier concentration in spite of any doping and everything else is EFI. EF equals to AFI. And let us look at what happens at T equals to 300 Kelvin. At 300 Kelvin, the Fermi level is halfway between the donor level and the conduction level. The first diagram, if you see this one, this is the first diagram which you see. If you look at the first diagram very properly, this ED is my donor states for level. And since the donor state level is very close to the conduction band, the donor can easily donate one of its electron to the conduction band, itself becoming a positively charged ion, and the level difference between ED and EC will be relatively very small. Let us look for an N-type semiconductor. What we are saying is, at 0 Kelvin, the Fermi level will be almost midway between EC and ED, or halfway between EC and ED. And this is quite interesting now, which means that the difference between the Fermi level and the conduction band is very, very small, correct? But please understand, your temperature has actually gone to 0 Kelvin, which means that at 0 Kelvin, since the thermal energy is 0, you will never be able to promote any further electron to the conduction band. This is for an N-type material. Let us go to a P-type material. What is happening in P-type material? Look at the bottom figure here. My Fermi level is midway between EA and EV. So let me write down here EF, right, at T equals to 0 Kelvin for an N-type material is given as EC plus ED by 2, right. EC is conduction band and ED donor state, and similarly we write down EF, right, at T equals to 0 Kelvin for a P-type material is given by EV plus EA by 2, halfway between the two, halfway between EA and EV, and in the first case halfway between EC and ED, which effectively means that, so as I discussed with you, the basic concept of Fermi level, all the states below the Fermi level are filled up, and every state above the Fermi level is actually empty. That is true even at T equals to 0 Kelvin, and you can see it is empty along the board in the top direction. Okay. Now let me just slightly deviate from that topic of cryogenics and explain to you what is a degenerate and a non-degenerate semiconductor, right. Now if your Fermi level has actually entered inside the conduction band edge. So what was the definition of the Fermi level? That all the states below the Fermi level will be fully filled up. Therefore all the states between Fermi level and the conduction band, which is shown by light blue color here, are all filled up. So these are all filled states. This wouldn't have been true had it been non-degenerate semiconductor, right. So I will give an example. How do I get this type of explanation in Fermi level? Let us suppose your device was initially intrinsic. Forget about temperature now. Just look at 300 Kelvin and assume that your device was fully intrinsic in nature. Therefore, EFI equals to EF equals to EC plus EV by 2, which means that my Fermi level is lying at the midpoint or the halfway in the band diagram, in the energy band diagram. What has happened now? I do a doping, I do a group 3 doping, right. So what happens? The intrinsic Fermi level starts to go down near the valence band, because the number of holes starts to increase, and therefore the difference between the Fermi level and the valence band has to reduce, and that's happening. As it goes down and down and down, I stop the doping at certain point of time, and I then do a reverse doping, which means I do an n-type doping now. Then what will happen? As I start n-type doping, the conduction band fills up, then the Fermi level starts to move up, right? Now, if there were, say, 100 holes being generated initially, then what will happen is, as the number of dopant species goes on increasing, say it was initially 10 electrons, then 20, then 50, 70, and when it is increasing, the Fermi level starts to move up. Exactly when the number of electrons in the conduction band is 100, which is exactly equal to the number of holes in the valence band, it again reaches the intrinsic Fermi level, fine, because the number of electrons and holes are exactly the same here. Now, if you go on increasing more and more dopant species, which are making it more an n-type, the Fermi level will start now to move up closer to the conduction band edge. There might be a case that the difference between the conduction band and the Fermi levels becomes so small that even at room temperature you have large amount of charge carriers being donated from the donor species to the conduction band. There might be also a case where all the Fermi level goes into the conduction band. In energy scale, the region between the Fermi level and the conduction band is fully filled up, right? This is known as a degenerate semiconductor. This is for n-type on the left hand side. Exactly same happens for p-type. It's easier to understand or the figure out for n-type, so I give an explanation. The same explanation holds good for p-type material when the Fermi level goes below the valence band. When it goes below the valence band, this light blue colored region is fully empty, and they are full of holes, right? They are holes, and these are what? These are electrons, correct? So what we have learned here is that I can actually design degenerate semiconductor by doing such type of movement of the Fermi level with respect to the band gap, right? Now, let me come to the p-type semiconductor, and let's take up again the same example. We are moving forward with degenerate and non-degenerate semiconductor. So, as I discussed with you that at T equals to 0 Kelvin, the Fermi level will be somewhere between the acceptor level and the donor level by 2. So, if semiconductor is fully p-type at T equals to 300 Kelvin, the Fermi level will be very close to the valence band if it's an acceptor ion concentration which I am feeding. So, the distance between the Fermi level and the valence band is very small. Please understand, the Fermi level will be halfway between the two, so the Fermi level will be still closer to the valence band. So, it is believed, and theoretically it is believed, that EF, the Fermi level, will dip into the valence band at T equals to 300 Kelvin, but that does not happen. I am assuming that what people saying is they are very close to the Fermi level, very close to the valence band, and they might be dipping into this. But please understand, there is another functionality happening. If you remember, I told you that at 300 Kelvin, I am assuming 100% ionization. Let's not, you don't look at this, we will come to this later on, but let us go one by one in each case. T equals to 300 Kelvin, right? I said 100% ionization is happening, which means that if I have a donor species which are 100 in number, all the 100 atoms are donating each electron to the conduction band, which means there are 100 electrons available. This is known as complete ionization. However, at T equals to 0 Kelvin, you will never have a complete ionization because the thermal energies have almost gone. So, not all the donor or acceptor species will be able to donate or accept respectively an electron. You got my point? So, if there are 100 dopant species available, maybe 20 to 30% will only become ionizing, and rest 70% will not ionize, which means that the number of electrons available will be relatively small, and therefore, the Fermi level will be slightly away from the conduction band. It will not go inside the conduction band. That is what is written here, right? Because of incomplete ionization, there is non-degeneracy even at cryogenic temperature, which means that I would have actually understood that if there would have been a 100% complete ionization at T equals to 0 Kelvin, I will actually get a degenerate semiconductor and I will be very happy. Does not work out because the thermal energies are so small, you end up having a non-degeneracy and even at cryogenic temperature, right. Let us come back to the right hand side sort of detailed energy level diagram. So I have a p-type silicon here, I have an oxide layer, this is a MOS layer, and this is the metal which I am talking about. Now if you see very carefully, my intrinsic is somewhere between EC and EV. What has happened is, if you look at this blue EF, right, this is EF is what? EF is as per 100% complete ionization. I had inserted acceptor ion, assuming that 100% ionization has taken place at cryo. This blue line which is below, there are two blue lines, if you see very closely, there are two blue lines. This is one blue line here, another is this blue line. I would have actually got EF. In reality, I get EF star. EF star is slightly away from the valence band. Don't look into other things. Other things are, you will get confused unnecessarily. The energy difference is given as Q times del phi f. Del phi f is the difference in the Fermi level in terms of energy. Del phi is in terms of voltages, actually electron volts. The amount of difference which you will get because of non-degeneracy in a semiconductor. So this is the difference which you get. You got the point? This is at 4.2 Kelvin p-type silicon. I would recommend you to please draw the same diagram. Right? I will suggest you or recommend you to draw the band diagram looking at this for an n-type silicon at t equals to 0. Correct? And that will give you an idea about degeneracy and non-degenerate semiconductor. So let us look at Fermi level and dopant freeze out at cryogenic temperature. What do you mean by dopant freeze out is that when you insert this dopant species, let's say 100 dopant species are inserted. The idea here is that if I insert the dopant species and none of the dopant species are able to contribute to an electron, we say that the freeze out has occurred. So if you look at with freeze out, then I will get EV plus EA minus EV by 2. You get the point? No, EV is here and this is my EA minus EV by 2 is my Fermi level. If you have dopant freeze, this is with dopant freeze out. Without dopant freeze out, my Fermi level will be clocked near EV, assuming that full ionization has taken place and all the acceptor species have been able to donate the holes, which means that the acceptor dopant energy influences the Fermi level, right. So let us again recapitulate this slide here before we move forward. The first thing which we learned here is that the behavior at low temperature, if you have a dopant freeze out means and no contribution is there, that means zero contribution of the dopant species to the or acceptor species to the semiconductor, then I get EV plus EA minus EV by 2. This is the point. This is your Fermi level with dopant species. Now without dopant freeze out, which means that there is partial ionization or even full ionization, then EF will be almost near to EV, will almost tend to be EV, and that is the reason I have shown you here. So in dopant, this is known as a dopant freeze out effect, right. So and that happens at a very low temperature. So accepted dopant energy influences the Fermi level shift to a larger extent, right, and this is a known fact overall. Now if you do a rough calculation of a standard semiconductor, it is being found out that EA minus EV by 2, let me show you how it works out. This is EC, this is EV, this is basically my Fermi level which is there. So this is my, let us suppose this is my acceptor level. Then this divided by 2 is the Fermi level which I would see is around 22.5 millielectron volt, and it is slightly larger than the thermal energy at cryogenic temperatures. At room temperature 25 millivolts, right, but at cryogenic it is much smaller. So if you take 4.2 Kelvin, then 3 kBT, kB is my Boltzmann constant, is approximately 1 millivolt, which is much smaller as compared to 22.5 millielectron volt. So the amount of thermal energy available to you, right, is much smaller as compared to the energy 22.5 millielectron volt, and this is where you apply the Boltzmann approximation for carrier concentration, right. So your Fermi Dirac is gone and you apply a Boltzmann statistics here, right, and the expression which you get is in the last part of this slide, which is this one. So I will not go into details of this one, not required for electronics engineer to a very large extent, but you should have the knowledge how it looks like overall, right. Now charge neutrality conditions tells you that the number of holes which you contribute from an acceptor ion. So if there are 100 acceptor ions being given and all the 100 acceptor ion gives 100 holes, then the number of holes P is exactly equals to the number of ionized acceptor ion which have donated one hole and itself become a negatively charged species. So that's the reason I've written P equals to Na minus. You see, P equals to Na minus, which means the number of holes is exactly equals to the number of acceptor ion concentration in the negative charge. Keeping that in mind, I get Ni exponential phi f star by ut, ut is kT by q, becomes equals to this complicated formula where Ga is known as the degeneracy factor. Right now, if we look at the Fermi potential, I will not go into the derivation of it, but let's look at how the Fermi potential will behave when you have a full dopant freeze out, right? And this comes out to be this quantity. This is the Fermi level potential. And so look at this point. This was originally the value of phi f, right? The phi f star with including dopant freeze out, you have a decrement by this much factor. You have a decrement by this factor, where ut of course is kT by q, thermal voltage. Phi of A, which is this quantity, this quantity phi of A, is intrinsic minus the acceptor ion divided by q in terms of this. So this was in terms of energy, this is in terms of voltage, and we take the factor of Ga, which is the degeneracy factor, to be approximately equals to 4, and all these are fed into this expression here at the below this one to get the fresh value of the phi f star. And if you look very carefully, the ut term is kT by q, it comes in the first term as well, in the first term here, and it also comes in the second term, right? And it both are sort of, I should say, same in nature. So what you can do here is, since ut is same, you take ut outside and you do ln Na by Ni minus ln of this big quantity which you see, this one, right? So it's basically ut by 2 which comes out. So this comes by 2, something will come out. This whole quantity is this quantity, which is quite interesting, right? Because as the value of ut is kT by q. So as the t goes on falling down, the ut factor starts to go down, right? We define ut as thermal voltage because it is kT by q. It's 25 millivolts at 300 Kelvin. So as the acceptor ion concentration increases, and this is for you to understand or you to react to, but as the acceptor ion concentration becomes larger and larger, this quantity increases and therefore this quantity drops down, which means that my effective Fermi potential will drop down as Na starts to increase. Please think about it, what is the reason for a decrement in the Fermi potential with respect to Na. Now let's discuss the Fermi potential qualitatively with description with temperature. And if you look at the first term is this one, this is the first term, right? And this is the second term. And if you plot the del phi f is phi f minus phi f star with respect to temperature for varying values of Na, then as the Na value is low, the change in the Fermi potential is relatively much larger for a small change in the value of temperature. So even when, and that's quite interesting, and this is where the actual cryogenics comes into picture, that as your temperature goes to a very low value below 50 Kelvin, you see that where Na was very small, so this curve let us take up, was very small, the drop is drastic, right? But when Na is 10 to the power 18, the drop is relatively small here. In fact, if you look at this place, the drop is very small. So if you draw a line here, as the Na value goes on increasing, the drop goes on decreasing, right? So which means that higher the acceptor ion concentration, lower will be the change in the Fermi potential available to us, right? So just try to think, why is it like that? First thing. The second thing is, at 300 Kelvin, if you look very carefully, the number of change in the Fermi potential is very large at 300 Kelvin, right? Not very large, it is relatively smaller as compared to that in the Fermi, in the very low Na region, right? So that is what we have learned, at least from this discussion. Let's finally come to the bulk Fermi potential. So two things which we are looking into. So the whole idea came into picture because you had an incomplete ionization factor coming into picture. Why incomplete? Because the energies are not high enough for the electrons to get generated and get contributed. That's the reason we define that to be as incomplete. So if you look at the right hand side figure, which has got temperature on the x axis, and you have phi f and phi f star. So phi f is the dashed curve, this dotted curve which you see, phi f Fermi level, and this solid lines are basically phi f star, which means that the with incomplete ionization with complete ionization. So this one is complete ionization, this blue colored dotted lines are incomplete, and this is complete. You see, I have written here complete, is incomplete. Don't go into details of this one, you will possibly get confused at the earlier stages, but two takeaways which you need to ensure is, first thing is at very very low temperature, there is a drastic difference in the Fermi level potential between incomplete and complete, and that can be seen by this red colored or mauve colored del phi f term here. As the temperature goes on increasing, since incomplete ionization falls over the complete ionization, so you see they tend to merge with both the lines merge with each other. The dashed lines and the solid lines, they merge with each other at higher temperature. Why? Because you are coming region from incomplete ionization regime to a complete ionization regime, right? And that's the reason you get such type of material. But takeaway from all this discussion is, around 0 Kelvin or very near to 0 Kelvin, you actually see change in the Fermi level between the incomplete and complete, and that is very very important. So the whole discussion for this lecture was to showcase to you that at very low temperature, because of incomplete ionization, the Fermi level will change, right? So let me recapitulate what we did in the previous half an hour. Is we learned about what is known as a complete and incomplete ionization. We learned about bulk potential and how these two are a function of temperature, both complete and incomplete, how they are function of temperature. We have also seen that as the temperature goes on increasing, the complete and incomplete, they merge with each other, and the difference is maximum near the cryogenic temperature. This we will carry forward in our understanding in the next slides. Thank you.